it's actually okay. We're going to go ahead and get started. Thanks for joining. I'm happy to introduce Andreas Prein as our speaker today. He's the Project Scientist 3 here at NCAR in MQ, and the Deputy Director of the Capacity Center for Climate and Weather Extremes, C3WE. He has his PhD in physics and a master's in environmental system sciences from the University of Graz in Austria. He's involved in many community activities, far too many to list. His research focuses on an improved understanding of the physical processes that change the frequency and intensity of extreme events in a warming climate. This includes changes in processes across all scales of motion, ranging from synoptic to microscales, with the main interest being convective extreme events, which is going to be the subject here. Go ahead and take.
You're welcome, everybody. I wanted to start with a beautiful picture of a derecho, and maybe many of you will remember this one, because if you look at the date, this was at the height of the pandemic. I can remember 30 minutes before it hit Boulder, there was a MoCast warning us there is a line of convection coming over, actually, from Utah. And it stayed very well organized, crossing the continental divide. And this was the derecho when it was in South Dakota. So it kept on going quite a bit. These are the kinds of storms that we will talk about today in this seminar. Just to give you a bigger picture, if you work in climate change and extreme events, this is a nice diagram. It shows you basically on the x-axis how well we understand the likely influence of global warming on extreme events. And on the y-axis, it shows you how well we can attribute those changes to global warming. So if you're higher up here, somewhere up here, extreme colds and extreme heat, we understand pretty well how climate change affects those extremes. But if you somewhere down here, it's way more difficult, and severe convective storms are really at the bottom. It's a really tough challenge, but I think nowadays, with increasing computational power and with advances in modeling, we can really make some progress there. And this is really the area where this talk is focusing on. I'm mainly talking like the severe convective storms are really important also from a social perspective. This is a diagram showing you estimated losses per year in the US from either tropical cyclones in orange or severe convective storms in blue. And what you can see with tropical cyclones, like if you have a big event like Katrina in 25, or if you have Harvey or Maria in 2017, you can see these big jumps. So those are really often $10 billion, $100 billion losses. Hail or severe convective storms are different, but they accumulate to very similar sums. So you have a more steady baseline because you have so many each year. But on the order, you have every year, you have at least $10 billion losses from hail and severe convective storms in the US alone. So it's a big insurance problem as well. What I'm focusing on is straight line winds. And straight line winds are all kinds of winds that come out of thunderstorms that are not rotating. Like, it's basically to differentiate between tornadoes and everything else. And there are three categories of straight line winds. The first one is microbursts. You might know those from if you fly with airplanes in the past. Those have impacted planes quite a bit. If you take off or land, you shouldn't get into one of those. This would be really bad. You can see very small scale fish. This is a nice animation. It shows really this ball of cold air just dropping down and spreading radially. Very intermittent, very small scale, 2 to 5 minutes. You can imagine this is really hard to observe. Like, how likely would it be to have a station right in the bottom there? So those are really not very well observed. And also extremely hard to model. Like, this is nothing I will talk about. Like, the modeling that I use today will not be able to capture that. You really have to go down to LES scales to model microbursts. The big brother of microbursts are macrobursts, and this is a nice example from Phoenix a couple of years ago, and you can see this is basically just a larger scale phenomena. So really large volume of air dropping down, and very similar, you can still see how the air is spreading radially here in this image. And then the category 5 type of straight line winds are derechos. This is what we started off at the title slide. And those are very large scale features, can be hundreds of miles in length, and they can live for many, many hours and impact many, many states over a long period of time. So typically, if we look at extreme winds in the US, there are two categories, and there are flavors of that, but typically we talk about severe wind gusts. Gusts are here defined as 3-second winds, and this is everything that's stronger than 25.7 meters per second or 50 knots. And this is basically when you start to see impacts or damage on the ground. And then we have significant severe gusts, and those are 38.6 meters per second or 75 knots. So then you get really stronger impacts. Like, of course, the stronger the wind speed, the more the impacts are. A nice resource that we have in the US is severe storm reports, and I guess many of you know those reports. I just wanted to show you a couple of summer days, sequential summer days, to highlight how frequent these straight line winds are occurring actually. So what you see here, tornadoes are in red. There are a couple of tornadoes. This is August 7th, 2020. Wind reports are blue, so those are typically the most frequent. And then you have hail reports in green. And you can see, of course, they cluster. So often severe convective storms produce various hazards at the same time. This is August 7, this is August 8. So you can again see different areas impacted, but again, clustered. This is August 9, and this is August 10. This was a big event. It's known as the Central US derecho. Started somewhere here, over here, and then moved over, again, many states over many hours. Caused a lot of damage, especially in Iowa. And I think I have the stats here. These were some of the impacts from this event. So really massive impacts on agriculture, but also power lines, trees falling down. And overall, the damage was somewhere over $10 billion, so a really big event. The wind speed got up to 100 miles per hour, which is a Category 4 hurricane in the middle of the country. So quite extreme event. If you look at the climatology, this is from the Storm Prediction Center here, of the ratios that are moderately strong between 50 knots and 64 knots. You can see they're really frequent all over the eastern US, especially in the southeast. They're quite frequent here, but also further west, where we have also the hotspot for tornadoes, for example. If you go to the more intense events, they are more clustered in the central US or in the high plains, but there's also still a quite high risk if you're further east. What really got me interested in this particular study was this animation. I worked with people at MIT that look at renewable energy production. So they were interested in winds, and I'm interested in extremes. And I thought, we had this 4-kilometer WRF simulation, which is a climate simulation. I will talk about this in a minute. And this downscales ERA 5, which is the 5th generation of reanalysis data coming out of ECMWF. So this is probably the most accurate reanalysis data that we have nowadays globally. And what I'm showing you here is 10-meter wind speed over the course of June 2012. And I hope this plays well also online. But you see really beautiful fluid dynamics. I really like to watch those. Just a couple of things I wanted to highlight. Let me see, this is June 11th. This is almost unrelated, but just to show you what you get out of these simulations. Of course, ERA 5 doesn't have an island here, but the island is really well represented in, it's there in the 4-kilometer simulations. And it seems like you get Kármán vortexes in the wake of the island, which is interesting to see. So the topography is way better simulated. But more important here, which really struck my eyes, was first of all, if you compare those two patterns, you see the large-scale pattern is very similar. Here we have high wind speeds, here we have high wind speeds, this area. This is what we want to do with this downscaling. So we really want to preserve the large-scale patterns, and we actually use spectral nudging here to preserve the large-scale patterns. But the downscaling is adding local scale and regional scale features. And a nice example, I think this should happen right now, here, for example. You can find them pretty frequently. An area of very high wind speed, which is related to an outflow region of a mesoscale convective system in the 4-kilometer version of the data set, completely missing in ERA 5. They're really not there. You can see these are very long-lived phenomena. Now it's triggering more storms. This was a little bit too far. Now it's in the Mississippi River Valley. Again, nothing is there in ERA 5. And actually, just the next day, you can see another one now here in Texas, spreading out towards the coast. So these are very intense wind speeds, and they're related to organized convective storms typically. Not all of those are derechoes, but they have very strong outflows and can cause a lot of impacts. Oh, yeah.
So would you call this simulation or this output on the right, is that a reanalysis?
No. I would not call, like, you could debate, like some people call it a reanalysis. It's spectrally nudged. It fits observations. I will show you the 2020 derecho, a comparison to observations, and it looks okay. But for me, if you would call this a reanalysis, you would have to do a more rigorous data analysis or a simulation. But it's a great data set. It is 40 years long. It's pretty homogeneous. So it's a great data set to look at mesoscale phenomena and how they might change over time. This is basically exactly what I'm doing here. So the simulation is called CONUS 404. It's really a successor of previous simulations that we did. This is coming out of the water system program and HAB and RAL primarily. CONUS is obvious, it's focusing on the CONUS. 404 stands for 40 years downscaled at 4 kilometer grid spacing. That's why it's called 404. It's published in BAMS last year. You can read more about it. As I already said, the initial boundary conditions and the nudging in the interior comes from ERA 5. It's continuously ran from 1970 till close to present. To finish this simulation, it takes more or close to a year. Like you have to be patient, but it's very well spun up after a couple of years. No explicit convection, so it's all numerically simulated. The model physics are down here, so those are fairly standard model physics, I would say, that we used since many years. One thing I wanted to highlight is we use a groundwater module in NOAA MP, which is very important. It helps a lot to better simulate the Central US summertime climate. And the data set is completely open, so it's on Glade if anybody wants to look at it, but you can also access the data set through RDA. This is just another view of how the simulations look like, comparing, again, the cloud field on the left side from this CONUS 404 simulations with observed clouds. And you can see the spectral nudging is doing a pretty good job. So the clouds occur in the right spot at the right time. Still I wouldn't call this a reanalysis data set, but you see it's getting close. So it's a pretty good representation of what we see in reality. It's not perfect, but it's really a step improvement if you're interested in mesoscale processes compared to ERA 5. So coming back to the 2020 derecho, these are a couple of snapshots of different fields that are important for these kind of storms. And we look at ERA 5 fields here. So the bottom one here, this is maximum CAPE. You see that it's very juicy. This is normally what you need for derecho specifically, lots of CAPE, lots of buoyancy in the low levels. If you look at the reflectivity field that ERA 5 simulates, it's very disorganized. Like it's basically just started convecting everywhere there is CAPE. And this is very well known for very coarse resolution modeling. Global climate models have the same issue. So even the data simulation doesn't help a lot there. If you look at the surface wind speeds, yeah, there's nothing. And the cold pull intensity, which is basically a proxy for how dense and heavy the cold pull is, there's also nothing there. So this is a proxy for how fast the wind speeds can be related to a cold pull. This is when we downscale the data set, and you can see a really big improvement. First of all, you nicely see the storm already ate quite a bit of a hole into the CAPE. So this is what normally happens. It really uses up the buoyancy when it goes along. There's a very well-organized line of convection, which was very similar to observed. We see the wind speed, 10-meter wind speed, very high wind speeds, very localized though. Like this is often also the case in this derecho. They're big phenomena, but the peak wind speeds can be extremely localized. And this is the cold pull intensity up here. So there's clearly a well-organized cold pull, which is quite intense in some spots. So again, a really big change from ERA 5 to the 4-kilometer CONUS. This is a Pullman's version analysis of this system. The left one is the radar. Sorry that I didn't pick the same color scheme. but you can see the structure of the system is reasonably well simulated. Also the location, it's a little bit displaced. But overall, it looks quite similar to what was observed, which is actually not the main intent of the simulation. It's not really intended to capture event by event. It's really more intended to have a long-term record of high-resolution data that we can leverage. So this is something we cannot observe, which I think it's really fascinating to look at these figures, at least for me. This is for just 1 month, August 2019. You can pick any summer month. It will look similarly. The peak wind speed, hourly peak wind speed over this month. So every hour we have hourly output. So every hour you save instantaneous wind speeds. And what you see clearly in here is you can nicely basically calculate how fast these storms are moving because you have this propagating cold pools, and you see the gust front moving from the west to the east, typically all over the place. Again, like using this data set is difficult if you want to do long-term statistics because we heavily undersample. Of course, if you look at like we have high winds here and high winds there because we have hourly output. Fortunately, we also saved the time step maximum daily wind speed, and this is the same field now, but with the Wolf time step 20-second maximum, and now you can clearly see this streaks of very high wind speed. So it's basically this propagation of the system from the west to the east. And again, like it's very localized. So it's really hard to observe these things because it's similar to precipitation extremes. Like they can be very intermittent and very localized. This is how this field looks like if you look at 42 years. So the color scale is a little bit bigger. What I also wanted to highlight, there's a tropical cyclone down here, just to highlight how the wind speed of the tropical cyclone looks like. Of course, you see the rotation in there. Here we see many tropical cyclones in the Gulf and in the Atlantic, but you can still see these streaks. Like still, even if you have 40 years, it's still very noisy data to work with. So keep this in mind. It's especially difficult if you think about observational networks that are not very dense to capture those extreme events. And this is the observational data set. I don't know who has experience with long-term wind records, but it's really difficult to find long-term records. And I wouldn't call them extremely reliable. So there are many issues with long-term recordings of wind speed. But this is the HAD ISD data set that I'm used here. And the region that I'm focusing on is in the central US. There are approximately 90 stations in there that have at least 80% coverage. And I'm only looking at June, July, August, so only summertime wind speeds. So this is the observation. And the color scale here is the long-term trend in wind speed. This is the annual maximum wind speed and how it changes over time. And you can see, like in this region, still from station to station, there's a lot of variability. So even if two stations are very close together, one could go up, one could go down. But if you do some statistics, and this is what I did in the background, I smoothed basically, or I pooled many of those stations in the region, you see most regions in the central US, and actually other places in the US as well, have an increase.
For that, for the maximum wind speeds, are you just using surface stations, or are you using, for example, severe weather reports?
I only use surface stations. Yeah, like the severe weather reports have different kind of issues, but I didn't go there. So I really tried to use the observations, the long-term observations that we have, the station records. Yeah. So it's 90 stations approximately.
Weather reports would show how localized it really is.
Yeah.
But yeah, I can understand that.
Yeah.
It'd be difficult to incorporate.
Yeah. So this would be the same plot from ERA 5. ERA 5 has no trend in maximum hourly wind speed in the central US during summertime, and this is what the CONUS 4.4 looks like. And then you see it's still very noisy, but at least you recover some of the trend that we see in the observations. One of the main questions that I got during the review process is how can you be sure that this is convective wind, if this is straight line winds or any other kind of winds? And the first thing that I thought of was I should check if there is a cold pool related to the wind speed. So what you see here, this is a different station data set that I used. It's the ASOS stations. We have way more ASOS stations in the central US. The nice thing with ASOS is we have multiple variables, but we also have temperature and wind speed at the same site. So what I did then is basically I just looked at the temperature drop and basically looked at the wind speed, at the temperature drop as a function of the wind speed. And you can see the faster the wind get, the stronger the drop is. So this is pretty clear indication that there are cold poles and indication that these are convective winds. The problem with ACES is those are not really long-term records. So you have those for a couple of years. So those are not really good for trend analysis, but they're good for more process-based studies. What you also can see, like the model is in red, the stations are in black. The model is underestimating the wind speeds. It's, I think, to be expected. It's a 4 kilometer model, so it's a 4 times 4 kilometer, and probably numerical diffusion is playing a role here. But you can see, like, generally the same behavior, but with lower wind speeds. The way I try to tackle that is to do something like a quantile mapping. So what you see here is PDFs of June, July, August wind speeds from the observations. This is the black line. And then the model, which is the red line. And I added, like, the observations are 60-second wind speed observations. And I added a gust factor, like another thing I did here, but we can talk about how reliable those are, but you can basically estimate the 3-second gust from the 60-second wind speed observations. And now you can basically say if you have 15 meters per second wind speed in the model, this relates approximately to 27 meters per second of severe wind speed observed. So you can say 15 meters per second, approximately severe wind speeds, where you start to see some impacts. And of course, this is a little bit hand-wavy, but just to convey, like, this is approximately the wind speed. Between 15 to 20, once you're down to 20 meters, you can say that's quite heavy wind that the model is simulating. Another thing that I did to make sure that this is coming out of thunderstorms is I basically looked at the cloud shields. So I detected cold cloud shields, the anvils, and said, only if wind is underneath the cloud shield can it be convective. This is what I did for the observations. For the model, I also had radar, or simulated radar reflectivity. And I also said, like, additionally, you have to be close to a high radar reflectivity area. So this is basically showing here, when you underneath the cloud shield, so this area would be convective wind. At least this is what I consider as convective. And for example, this area down here is not convective because it's remote from the anvil and it's remote from high reflectivity areas. So if you do that, you can get two time series. You can get a time series of wind from thunderstorms and a time series of wind for everything else. This is what I'm showing you here. So this is the long-term record, 40 years of observations now, these 90 stations that we have. And you see that the black line is the non-convective wind speeds, which are fairly flat. First of all, they are lower than the red line, and they are fairly flat. And then the red line is everything that's close to convection. This is clearly going up significantly over the last 40 years. And they are more intense. What you see in the middle is basically how, if you have these 90 stations in the central US, how often is the annual maximum a convective extreme or non-convective extreme? And you see at the beginning of the time series, 2/3 approximately were coming from convection, and this is increasing over time. So extreme wind speeds are getting more and more dominant from convection in the central US under current conditions than in the past. And this fraction of convection to non-convective wind speeds is highest in the southern region, southern part of this central US region that I focused, and it's lower in the northern part, meaning the northern part has also more contribution for other kinds of wind speeds. This is what it looks like from ERA 5, and immediately there are two big issues here. First of all, the convective extremes wind speeds are lower than the non-convective, and then both of them are flat. So this looks really like wouldn't be a good data set to study how these things change over time. However, if you look at the CONUS 4.4 data set, you see we recover some of the signal. It's not perfect, but we are getting much closer to what we have in the observations. I want to highlight, like, the observations have a stronger trend, approximately twice as strong than the model. So it's going up quite a bit. Some reviewers had concerns, again, concerning the intensity of those winds. But of course, if you look at the intensity, those wouldn't be winds that cause damage. That's true. This is the annual maximum in summertime. And I talked at the beginning, like, it's very, very unlikely that you really measure one of these high wind speed events, especially if you have only 90 stations. So you get fairly low wind speed. So what I did then is I tried to plot the trend of the wind speed as a function of the speed. So this is the change in the frequency of how often wind speed occurs over the 40 years as a function of the intensity of the wind. And first of all, you see again, like the black line, this is non-convective extremes. They don't really intensify even for high intense wind speeds. But the second one, the red line, is showing you that especially the most intense wind speeds are increasing in frequency the most. And those are really, really high increases. So this is more than 20% per decade in frequency increases. So this is a very strong increase that we see. The model, again, like does quantitatively something very similar, but the trend is a little bit muted. And then I also had this picture in the paper, which I got a couple of comments back that this is really hard to verify, and I'm not sure if this is true. This is what the model tells you. If we look at grid cells that have more than 20 meters per second wind speed over time, so you just accumulate how much area is affected by 20 meters per second wind speed every summer season, you can see a very strong increase, which basically it's a five-folding over the time period. Of course, this is extremely hard to verify if this is true, but we see at least from observations also that the most intense wind speeds seem to be increasing in frequency the fastest. So the key question now is this climate change or not? That's a tough question to answer. So we see the observations and the models telling us a similar story, like wind speeds, convective wind speeds are intensifying. The way I approached this was to try to look at environmental proxies and say, okay, how are environmental proxies related to extreme wind speed in the central US? And this is, again, similar graphic that I showed before. These are now for each thunderstorm, the maximum wind speed in the outflow. And this is over time. You can see this is clearly increasing over time, the wind speed. You can look at the cold pool intensity. I talked about this at the beginning. So it's basically how dense the air is and how deep the cold pool is. And you see a very good relationship between the actual 10-meter wind speed. This is all simulated now, by the way. The 10-meter wind speed and the cold pool intensity. This is extremely high correlated. Just basically reinforcing that this is really convective wind that we're looking at. But the cold pool intensity is not a really good environmental proxy because it really depends on already having a thunderstorm. So you have to get the thunderstorm first to create the cold pool. The proxy that I went with is the maximum downdraft wind speed, which is related to the downward cape. And I will talk about this in a minute. This is the red line, and you can still see a fairly good correspondence between the downward cape in the inflow environment of the thunderstorm and the wind speed that comes out of the thunderstorm. These are just correlation coefficients showing that all of these that are tested cold pool intensity, downward maximum wind speed, the decape, the shear, the downdraft at 91 meters, and the maximum upward wind speed, which is basically cape, twice cape, the square root of 2 times cape. And you can see all of them are significantly correlated with the wind speed. So just basically saying, and also interestingly, all of those are correlated as well. So you can, for example, see that the cold pool intensity, if I can find the mouse, the cold pool, now I'm getting lost. Maybe I walk over. The cold pool intensity is heavily correlated with the wind shear. It's just saying that all of these processes are interacting. You have to have all these processes happening at the same time to create extremely high winds. But as I said, I went with the downward cape, and this is how you define downward cape. Everybody that's familiar with cape, convectively available potential energy, should be familiar with what this is. It's basically cape put on the top. So what I'm doing here is I'm looking at the minimum dew point temperature in the layer between 800 hectopascal and 600 hectopascal. And then you find this area where the minimum dew point temperature is. You saturate the air parcel, and then you basically descend the parcel along a moist adiabat. And decape is then the area between this moist adiabat and the environmental air. There's a virtual temperature correction there as well. So the larger decape, the stronger the potential downdraft can be. And this is the formula that you can, like it's the square root of twice decape is the maximum downdraft speed, the theoretical maximum that you can get. So to understand how climate change might impact decape, I did very simple analysis. This is a composite sounding of the ratio inflow environments. This is from Doswell. I forgot which paper it was, but Doswell published this a couple of years ago. And you can see decape is basically shown in this blue area down here. And I changed just this sounding. I changed the temperature, relative humidity, and the stability of this. These are all things that we know that these environmental proxies are changing with climate change. So first of all, temperature, of course, is increasing with climate change. So if we just shift the sounding to the right, increase the temperature, the effect of this is basically that you get a steeper moist adiabat, and the virtual temperature correction is larger. So you increase the decape if you increase, just by increasing the temperature. This is the same reason why you increase cape as well, like this steepening of the moist adiabats, and this is fairly well understood. Secondly, relative humidity. Relative humidity basically means the dew point line is shifting to the left. What this means is you get a drier, a lower saturation mixing ratio of the downdraft parcel, and this is also increasing decape. There will come to some caveats with this whole thing at the end. And then lastly, the stability. So we know climate change is increasing the temperature faster in the mid-levels than in the low levels. So it's basically making the atmosphere more stable. So you basically just tilt the whole sounding, and this has a decreasing effect on decape. So I did all of that systematically by, I can show you this, it's maybe a weird plot to look at, but what I did here, I changed temperature, stopped working. I changed temperature from -2 degrees to +4 degrees, the relative humidity from ±6, and the lapse rate by -0.25 to +0.25. And it's very obvious what the dominant factor here is, how decape is affected. It's the temperature. So if you, for example, this is a slice through this plane here, so changing only lapse rate and relative humidity with keeping the temperature constant, there's very little impact on decape. But if you change the temperature, this is up here, so the temperature's in the bottom, you can see per degree warming, you get approximately a 7% increase in decape. And that's maybe also not surprising, because if we look at this is mostly related to the steepening of the moist adiabats. So the moist adiabats, which are these lines here, this is still not, oh, it's coming back. So these lines, and this is really too difficult for me, these green lines, you can see they're flat here and they get steeper and steeper as you get to higher and higher temperatures. And this is the equation I used to calculate the moist adiabat. And what you see here basically is this dependency of t to the power of 2 down here and t up here. So the warmer the temperature gets, the smaller this factor gets, and the steeper the moist adiabat gets. And this red equation comes basically directly out of the Clausius-Clapeyron relationship. So we know that the saturation mixing ratio is increasing by approximately 7% per degree warming at around 20 degrees Celsius. So this is just to show you how the moist adiabats depend on the surface temperature. If you have 10 degrees, for example, you get a moist adiabat of -6 Kelvin per kilometer. If you're up to 40, you only have -3. So there's a quite strong temperature dependence here, and this is the main reason why the decape is increasing. However, decape is not a really great proxy, I have to admit. So the first thing, decape it's already in the title, it's the potential energy. You have to realize the energy. So first you really have to trigger convection, and then you have to create the downdraft to really get the wind speed out of these storms. I think I have this in the second slide. Relative humidity, it looks like it's beneficial to dry out the atmosphere because you get more decape. And actually, if you look at decape in the US, often you get extremely high values in the desert Southwest. Of course, there's almost no chance for a thunderstorm in these environments. It's extremely dry, so you cannot realize the decape. So drying in the future might also mean more suppression of severe convective storms. So just another caveat. Defining the parcel is really difficult. I think it's more difficult to define the downdraft parcel than the updraft parcel. So it's really, I tested quite a couple of things. I spent weeks on the decay calculation, and it's not trivial. There's also very little code available to do this, actually. And then entrainment, of course, like a completely neglecting entrainment in the downdraft parcel. So normally you get dry air entrainment, and this is slowing down the downdraft as well. Just to sum up, this is a summary that I put in the paper at the end. So the main message here, you get stronger downdraft because you get enhanced evaporative cooling in a warmer climate when the downdraft comes down. This is increasing the cold pool intensity. This is mainly because of the steepening of the moist adiabat. So these are these lines with warming. And there's also a slight contribution from an increase in this virtual temperature correction that you have to do if you have more moisture in the air. Just a couple of take-home messages. First of all, I think kilometer scale modeling, and I think I'm preaching to the choir here, like we use this kind of models since almost 3 decades now to do weather research. But they're really allowing, in climate timescales, allowing you to look at phenomena that you couldn't look at in the past. I think it's really opening up a whole area of research where you can do, for example, look at severe windstorms, but probably also other, like extreme rainfall is another topic, or even hail, where it's way more difficult to do this in coarse resolution climate models. There are multiple lines of evidence that severe convective or straight line winds are intensifying, at least in the central US during summertime, due to warming. We see this in the observations, we see this in the model, and there's some theoretical evidence as well. So we theoretically understand why this is increasing. However, I didn't talk about changes in dynamics at all. That's a big question mark. This is normally, if you look at climate change, everything that's related to dynamical changes is way more uncertain than thermodynamical changes. So how mesovortices might change or rear inflow jets might change is really an open discussion. And those are really extremely important processes, especially in the most severe derecho storms. And just at the end, like I think it's likely that climate change will intensify straight line winds, but there are certainly open questions to look at, and I think there are more studies to be looked at to get a conclusive answer to this question. And with that, I want to thank you, and I hope there's some question time as well.
Okay, well, your wish is granted. We have a ton of time for questions.
You said something like, of course, the relative humidity is decreasing at mid-levels for climate change. It wasn't obvious to me why.
It's low levels.
Where the decay originates?
So the mid-levels, that's a good question. I'm not sure. Like I'm literature, and we see this in observations as well. Like the land areas are drying due to climate change in relative humidity terms. Like absolute moisture is increasing, but relative humidity is decreasing. But this is mostly close to the surface. If the mid-levels dry, I don't know if there's a systematic signal. No, I don't think that this is the case, actually. But again, like this is, with these storms, it's often remote moisture sources as well that play a role. So how these change is, it's yeah, another open question.
Thanks, Andy. That was great. And yeah, there's lots of stuff to explore here, but I'm going to back up to something that probably isn't as important, but I thought it was really interesting, showing the decrease in the percentage of convective straight line winds as you go up into the northern plains. Mm-hmm. And one of the things I was wondering, how much did you look at the sensitivity of your criteria? Because we sort of have a bias towards like Oklahoma storms and how we define our thresholds on what is the criteria for convective storms. Like as you get out of that southern plains region, storms can be quite severe and actually look quite a bit different. So I was just curious if you thought much about that.
That's a good, like I know there's literature on this as well that shows something similar, but probably runs into similar issues. Like the criteria, at least in the observations that I used there, was just, is there a cold cloud shield? So is there an ice envelope on top of the wind? And if not, it's not convective. So it's more often in the northern plains, there's no anvil on top. But of course, like you could also have propagating cold pools outside of these areas. And yeah, I didn't look into the details there, but that's a good point.
Yeah, I wanted to make sure Hugh got his exercise in today. Did you look at the time of day at all? Did you see any signal? Like, is this increase more at night or more during the day, or was it just all times of day?
Yeah, I didn't look at that, but that's a great question. Yeah, I didn't. Yeah.
Just curious.
Yeah, like the nice thing with the model, like once you have a 4 kilometer model, as you know, like you have data everywhere and you can look at these things nicely. But yeah, it's a good question. Yeah.
Yeah, actually, I have a quick question on the technical side. So you said there was some difficulty in defining the parcel for your downdraft calculations. Was that the initial conditions, or what? Like, what was the main challenge of that?
Just how to find, like, what is the source height of the downdraft?
Yeah.
That's the question. And then, if you look at literature, there are different people use different things. Like the minimum theta E is often used. I use the minimum dew point temperature. And then again, like it's also arbitrary to say it's between 800 and 600 hectopascal. Like just like you could use the freezing level high. You know, like there's, and I tested some of these things, and at least the core conclusions were the same, but results are quite sensitive to how you define the downdraft parcel. Yeah.
Yeah, I think that just gets to the general uncertainty of downdraft dynamics.
Yeah, which is actually not very well simulated in models anyway.
So there's a question here on Slido. Thank you for the fascinating presentation. I'm curious about the role of spectral nudging in accurately simulating observed weather extremes. How essential is it?
I think it's important. Yeah, I think if we wouldn't have done the spectral nudging, I would guess the results should be the same. Like what we did is basically we nudged everything above the boundary layer, like all the state variables except of moisture. And we nudged every hour, so quite frequently. So it's quite a strong nudging that we applied. And it really helps you to get storms that look similar to what were observed. We have other data sets, like similar 4-kilometer WRF simulations where we didn't use spectral nudging, and you get the MCS frequency, for example, in the central layers is very similar. So you probably get like you probably wouldn't get a good correlation between years where you have higher, like a higher frequency of high wind speeds in the model and the observations, but I think the long-term trend I would hope would be the same.
All right. Oh, a whole bunch more questions. Okay. Oh, then look back behind me.
Yes, this is a statistical question. You mentioned that the biggest increases were with the most extreme events. How does that compare in absolute numbers? Because there would be fewer extreme events, obviously, and there must be some sort of distribution of wind events.
Yeah, that's a good question. Like the diagram that I showed, I basically binned the wind events. So I said everything between, let's say, I don't know exactly what the boundaries were, but let's say 13.5 to 15.5 meters per second. How often are those events measured per year in the 90 station network? And then I just looked at the frequency, like you have maybe 10 in 1 year, then you have 15, 16, and then I calculated the trend. So I had a minimum sample size there. So this is why I cut off, like I didn't go out to 20 meters per second because those are so rare that you couldn't do any statistics on. I tested how big the sample size had to be. I cannot remember from the top of my head. I guess it was around 20, 30 events per year on average that I required to have in there. But again, like if you extract that, I did that, like it's getting extremely noisy once you get out to, if you only observe 1 or 2 events per year, it's almost meaningless to look at that trend.
Thank you.
Yeah.
I was wondering if you had an explanation for why the area of the straight line wind events are increasing. Is that due to the fact that some simulations have shown an increase in the convective area in storms in a future climate? Yeah, I'd be curious to hear what you think.
Yeah, so like the area and the frequency increase are of course linked. So what I see in the observations as well, like the frequency of this very intense winds is increasing, which means there are more stations affected by these extreme winds, which means the area is getting bigger. So I think there is some observational evidence there. I actually didn't, like the model would allow us to do this, to see if it's the same number of events that we have, but they're getting bigger, or if it's more of those events, but the size stays the same. I didn't look at that, but this would be actually interesting to do.
I thought we were trying to give Hugh exercise. Come on. So I had kind of a two-part question, and I see James Pinto has a question up there that's actually part of one of mine. So I'm going to acknowledge that he's asking a similar question, because I was curious how much temperature change you have been seeing over this region in the 404 simulation. And part of the reason I was wondering that too is in the earlier versions of CONUS 1 and stuff, there was a warm and dry bias in the central US, which I know the groundwater parameterization is meant to kind of help account for that. But do you still see any warm and dry biases in 404? And the only way that that could be relating here is if there's a trend in those biases, which I don't fully understand why there would be. But I just wanted to ask what your thoughts are and if there's any of those biases that could be playing a role.
That's a good point. Like approximately there's 1 degree warming. So, which means the model is approximately showing a 7% increase in the intensity of extreme winds, which is going back to the Clausius-Clapeyron scaling. The observations have twice as much, 14%. So it's, this 1 degree is a nice, like it's nice because you can immediately calculate. There is still a bias, it's way less intense, and it doesn't change significantly over time. But it's the central US, especially if you go a little bit further east, it's still too dry and too warm in the simulation. So this is still there. I think it doesn't affect the trend too much, but yeah, like the bias is still there.
Yeah, if the bias isn't showing the trend, I was thinking that might not be, but it's curious what that impact could be in here.
Yeah, yeah. And the bias is most intense in August and September. So yeah, but like it's not perfect. Like the simulation is not perfect. It still has biases, certainly.
All right, we need a mic stand set up in the back, I think. Okay, so one more question on the Slido. Thanks for this very interesting study. Do you know how much this increase translates into changes in return wind speeds, e.g. 50-year return period wind speed for severe convective straight line winds? Can this be estimated directly from theory? Are there implications for design standards?
So I actually talked to, I forgot how they call it, like there's a panel that looks at severe wind speed, an engineering panel. I talked with them, and they were very interested in the simulations. And like in theory, you can derive these return values. I didn't do that. 50 years, there will be, like normally what you do there is you fit an extreme value distribution, and then you can estimate an uncertainty bound. We have 40 years of data. There's a trend in the data, so it's not stationary, so you have to account for that. And my guess is the 50-year return period would be extremely uncertain with 40 years of data. So I would say 10 years, I would be more comfortable with saying something about 10-year return period, but 50 is still really challenging to estimate. You can do it, but yeah, I didn't do that.
Okay, one more. You can also link straight line wind impacts to convective momentum transport from upper level winds. Any thoughts on the effect of that simple dynamic mechanism with respect to climate change trends in the 404 too?
Yeah, thank you, Kelly. That's a great question. I didn't look at that, but this would get a little bit closer to these dynamic impacts that I talked about at the end. This would be actually something fairly easy to do, to look at how the momentum is mixed down with the downdraft. So this is more the rear inflow chat that we're talking about then, yeah.
All right. If we don't have any more questions, we can wrap this up. Let's thank Andy once more.
Thank you.